What is up? It's going down. I didn't check to see if my connection strength was green or red. But it's only going to be, the C++ hour. Gonna get this. We're gonna do this. Then we're gonna move on with our lives. Headset. You need to go somewhere. You need a living space, really. Headset. That would be cool. But I have nowhere to attach. See, I can't use my armrest while I'm typing if my headset's there, can I? Maybe it can like Scooby-Doo into the crack. There we go. Hi, welcome to the C++ stream, where I stream me doing C++ for exactly 1 hour, usually less than an hour, every Monday. At about 4 hours ago, usually. But I don't know, I woke up late, stuff happens. And that is... I've just seen the word Bitwise on my screen, and that means we're going to stop right there. Thank you for watching, everybody. I'm just kidding. Program that distinguished between high pass, pass, and fail depending on the fact that the conditional operator is right. So we did all that. Bitwise, we're on to the Bitwise operator. We are on to Bitwise Operators. Please stop rotating my screen. I want port landscape mode. Thank you. Just let me put that. You have no idea. Like, I need a stand for every goddamn screen in this place. I need a goddamn stand. This keyboard still needs to come over a little bit. Oh, I need to move all this stuff. It's stuff that doesn't even need to be here, really. So what we are gonna do is comment out all of the previous sessions stoof. Minimize it. Make sure. Alright, yeah, okay, let's. Give ourselves a heading for the new topic. Save. Welcome to the mouth noise stream. It's a very quiet cup to drink out of because it's got a very thin wall to it. It's a Spieglau stemless crystal wine glass. I just have juice in it though. Can't be getting lit when we're trying to learn stuff. I learned that lesson the hard way. Bitwise operator takes operands of integral type. They uses a collection of bits. These operators let us test and set individual bits. This sounds dangerous. You can also use operators on library type named bitset that represents a flexibly sized collection of bits. Oh, that's nice. As usual, if an operand is a small integer, its value is first promoted to a larger integral type. The operands can be either signed or unsigned. Okay. Okay, we've got a list of bitwise operators, and we have a list of how to use them. And so these what is XOR? What is it? I don't even understand what an XOR is. I'm sure I forgot to check something last sesh that we did and I didn't understand. Whatever. So bitwise not is a tilde. Left shift and right shift are left arrows, right arrows, those kind of things. Stop removing my tabs, please. Visual Studio, remove one more tab. Swear to God, I'm gonna uninstall you. We'll do this in fucking Notepad. We won't do this in Notepad. I'm not compiling programs through the PowerShell. God damn. I'm beyond that. I just want to click a button and have the program come out the other side. What? So, is that bad? Am I wrong for wanting this? Anyway, Bitwise AND is just a symbol. It's just a single ampersand. Bitwise XOR, whatever that means, is an upward arrow. Bitwise OR is a single vertical line. Come to think of it, it's really annoying for me, right? To look at this keyboard sometimes, like the Razer Black Widow keyboards. They have obviously secondary characters where you'd have all your secondary characters. You know, so you got your left arrow, right arrow, question mark, colon, at, tilde, curly braces, etc. And all the stuff on the num keys. It's not cut out. You can't see that in the dark. You have to memorize that stuff. And you know what? Sometimes I don't. Sometimes I can't see them. But it's double annoying because home, page up, page down, and end, insert, delete, enter, and numlock are all on the numpad. And it just would have looked like a nicer keyboard if you'd done etching instead of printing on those. It would have also been cheaper because you'd be down a process. You wouldn't have to paint any of the keys. You could just etch them. The function button as well. I don't even know if there's a backlight underneath the function key. I think there is, but why isn't it see-through? Anyway, rant over. If the operand is signed and its value is negative, then the way that the sign bit is handled in a number of the bitwise operations is machine dependent. Okay, fuck. Moreover, doing a left shift that changes the value of the sign bit is undefined. Okay, so don't do that. We've learned our lesson instantly. Do not mess around with negative values. We've already used overloaded versions of the right arrow and left arrow operators that the IO library defines to do input and output. The built-in meaning of these operators is that they perform a bitwise shift on their operands. Okay, they yield a value that is a copy of the possibly promoted left-hand operand. Okay. The bit shifted as directed by the right-hand operand. The right-hand operand must not be a negative and must be a value that is strictly less than the number of bits in the result. Otherwise, the operation is undefined. The bits are shifted left or right with arrows. The bits that are shifted off the end are discarded. Oh, fuck. I'm just looking at this example, and I don't get it. These examples assume the char has 8 bits and int has 32 bits. Okay. 8 times 4 is 32. So there's 4 blocks. I see. Right, okay. So unsigned char bits is equal to 0233. An octal literal. Right, yeah, and that selects character 233, whatever that is. That's how that works, right? But when you do bits left shift 8, I don't understand how it's promoted to an int because it's a char, right? Or is it promoted to an int because it's a char? Because without it being a no, I don't understand. What? Why? Left hand operand, the right hand operand, the left hand operand. Wait. So I understand what it's doing, right? It's promoting a series of good slam, a series of bits to an int, which increases the size of the bits, which increases the number of bits held in the information of bits to 32 bits. So the data stored in bits is put all the way at the right, but that's not what it says underneath this diagram. It says that the left shift operator inserts zero value bits on the right, or actually, does it do that when it shifts? It doesn't do that when it sets up the shift. So if you have a block of 32 bits, it's not going to put what you put in as I see. So it does it all in one go. Just for brain purposes, it does it all in one go. If you have an 8-bit thing and you do left shift 8, it will promote that to an int, which for this purpose is 32 bits. So it will populate a thing. Will it populate? I don't know. It will give you a thing with 32 bits. It will move your 8 bits left. It will put 8 0 bits to the right of your 8 bits, and then it will fill the rest of your bitwise return value with zeros. Okay, that's fine. That's brain correct. And if you move it 31, everything is discarded except for the last value of your bit sequence, which in this case is a 1 or a yes. Okay. Left hand operator is unsigned. The operator is a 0 values on the left. Sign type. The result implemented is implementation defined. Either copies of the sign bit or 0 value bits are inserted on the left. Copies of the sign bit. That just look messy, really, wouldn't it? Okay, I kind of get it. I don't know why you'd use these, but I guess we'll learn that in the chapter. 14 minutes, and I'm already wanting to not be here anymore. God damn it. Bitwise not operator, tilde, generates a new value with the bits of its operand inverted. Oh, that's cool. No, that is cool, because for the ANSI character set, something, they're something. Oh no, they're not. Never mind. Ignore me. They're up by one bit in the thing, but they're not flipped. So this flips bits basically. So the not operator also inverts any bits which are added in the conversion process. Cool. The AND, OR, and XOR operators generate new values with the bit pattern composed from its two operands. So B1 is 01100101 and B2 is 10101111, and it seems to the AND seems to preserve any zeros in the chain. The OR seems to preserve any ones in the chain, and the XOR preserves ones unless there are two ones, in which case it puts a 0, and it preserves zeros if there's two zeros. Why? Who built these tools, and why do we need them? Let me just move my microphone again. Everyone loves this part of the stream where I block my own view with the microphone. Make loads of squeaking noises. Okay. So AND preserves zeros, OR preserves ones, XOR preserves ones and inverts double ones. Why do you need these? What? Why? Why would anyone want to do this stuff? The bit is 1 if either but not both operands contain 1. Otherwise, the result is 0. Yeah, we'll go okay. Yes. Okay, we're going into a real deep brain example. This is so it seems to be that the book is giving us an example where we're storing bit information, basically a set of bools stored in a long, and then essentially we're using a long to store bit information that would otherwise be stored in an array or vector of bools, kind of thing. So basically they're initializing a long, and then they're altering the bit at a certain position of the long to represent the pass or fail qualification of a student in a classroom. And I get the big brain feeling that bitwise operations are for extremely limited memory situations where you can't have vectors or arrays because your computer system is so small that you can only have, well, I guess you could have arrays and vectors, but because they can store other information, these are literally just ons and offs. But I guess you could have extended ones that test a larger sample. This is only testing 1 bit at a time, and those bits are in a position, you know, are in a position in the long. Yeah, that. Cool. But I guess this is really small stuff because we're dealing with single bits, not bytes. We can obtain a value indicating that student 27 passed by using the left shift operator and an unsigned long integer literal 1. Alright, okay, so we have an unsigned long integer literal 1, so a long unsigned long equals 1. It is 1, assign it to 1, and then what? I'm gonna read this again. What the hell? Define quiz 1 as an unsigned long, thus quiz 1 will have at least 32 bits on any machine. Explicitly initialize quiz 1 to ensure that the bits start with well-defined values. Okay, it's equal to 0. Okay, teacher must be able to test individual bits. For example, we'd like to be able to set the bit corresponding to student number 27, indicate that the student's passed the quiz, indicate that the student number 27 passed the creating value. There's only bit 27 turned on. If we then bitwise or that value with quiz 1, all the bits except bit 27 remain unchanged. Yeah, so an integer value 1 is going to be a bit, all high order zeros and then a 1. And then if you do a shift, you can do a bitwise shift 27 to move that 27 bits to the left, which will give you a bitwise tool to access the information at position 27 in your original unsigned long. Quiz 1, yeah. Oh, and you can use the bitwise operators as compound assignment tools. Great. So quiz 1 or equals 1 UL will update quiz 1's position 27 to a 1. If it was 1 in the quiz and growly and or 1 in the current result. Cool. Quiz 1 is equal to quiz 1 or UL, 1 UL. Left shift 27. Okay. Wait. So, wait. Does the bitwise shift operation does that permanently change the value. Oh, let's just do what they're doing. So let's have a look. Oh, it doesn't. It does not permanently change the thingamajiggy. So if we wanted to see that, we'd want... Oh, sugar. Gonna have to... parentheses? Please don't get angry with me. Yeah, there you go. Okay, so we've got to use the... Wow, that's a big number. So the bitwise operators have to be... please. Why are you like this? We got... Do you not understand? Thank you. So bitwise operators only operate one time. They return a value to be used in that instance, and then they disappear. Of course they do. I'm an idiot. Said at the start of the chapter, bitwise operators return a copy of the value. Idiot. Brainhead. Big brainhead. Yes, you'd have to use an assignment operator. You'd have to use an assignment operator. So if we did bitboy, is that legal? Yeah, okay. So it's pretty cool how that worked. And then yeah, so to change the value of the int, you have to use an assignment operator in your bitwise operation. Cool. Right, okay, I understand it now, yeah. And then they've got this here, quiz 1 and equals not 1UL left shift 27. So it's gonna add, wait. Did and do again? It adds all the zeros. Yeah, and adds all the zeros, or adds all the ones. Zor is just a fucking weirdo. So that is gonna add a 0 at position 27 because you're adding not, and not makes all ones zeros and all zeros ones. You get a 0 at 27, you get a 1 all across the rest of the bits of the long, and that's good. So it doesn't add any ones, but the 1 0 that you have at position 27 because the child failed their test, their examination. that does the thing. Excellent, great. I get it. I kind of get it. I kind of, yeah. Bool status equals quiz1 and 1UL. An AND value that has bit 27 turned on with quiz1. The result is non-zero. Bit quiz1 27 is also on. Otherwise, it evaluates to 0. Bool status equals quiz1 and 1UL left shift 27. That's great. That's fantastic. So it compares. It doesn't compare. It doesn't compare anything. It adds and 1. So if yeah, so it will return yeah, what? 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 Why? What? Why? So we're bitwise ANDing, and bitwise ANDing adds zeros. So we're adding a 1 to quiz1's position. Oh wait, no, wait. Yeah, we're adding a 1 to quiz1's position. So if it's a 1, it's fine. If it's a 0, it's not fine, but I'm just gonna take it that works. That it's gonna get that 1 bit, and if it's 1, it returns a 1, and if it's a 0, then it returns a 0. I'm just gonna have to brain with that one a second. Shift operators and IO operators are left associative. Okay. Whoa! Dog! Whoa! Dog! Stop! That's not mine. That is someone else's dog. I think you can even hear that, can you? I had a little cheeky recording session where I, recorded some slamming doors. They're actually a lot quieter than I thought they were, so shows me, I guess. Shift operators are left associated with his expression. See out high there, Endel. Executes as see out high, and then there, and then Endel. Shift operators have mid-level precedence, lower than arithmetic but higher than relational assignment and conditional operators. These relative precedences means that we usually have to use parentheses to force the correct grouping of operators with lower precedence. See out 42 plus 10. It's fine. See out 10 is less than 42. Okay. See out 10 less than 42. That doesn't work. So write 10 onto see out and then compare the result of that operation, i.e. see out, to 42. Okay. What is the value of tilde q left shift 6 on a machine with 32-bit ints and 8-bit chars that uses Latin 1 character set in which q has the bit pattern 0111 0001? Tilde q tilde is not, right? So that's 1001110 6 over. So it's that's right? I made a boo-boo. Try it one more time. We'll write out what we know it's gonna be, and then is this still bound to mute mic? No, it's not. Okay, thank God. So that's fine. Let's start at 6. There you go. There it is. That's the value. And what do you mean what number is that? 1 2 4 sorry, 1 2 4 6 8 16 32 64 128 256 plus 256 plus 5112 plus 1024 plus 2048 plus 4096 plus 8192. Nine 9088. Why am I putting an E on the end of that? It's negative 7,296. Why? Why is it negative? Because it's a char? Maybe? Huh. Cool. Whatever. Now, grading example in this section, what would happen if we used a unsigned int as the type for quiz 1? You'd go past the left end of the, or you might go, you introduce the risk of going off the left end of the bits, which returns an undefined value when you do stuff that's left shifted 27 positions. What is the result of each of these expressions? Unsigned long u1l ul1 equals 3. Unsigned long 2 is 7. We got that right. We got 3 and 4, 2 and 1, 7. Hate binary numbers. They can fuck off. So we got 3 and we got 7. UL1 and UL2. That will be 3. UL1 or UL2 be 7. UL1 and UL2 what? I think it would be something like this, wouldn't it? It'd just be true. It'd just be 1. Because they're both non-zero integers. Right? We'll try it. We'll just try it. We'll just equals 3, UL2 equals 7. So we're looking for 3, 7, 1, and 1. C out. This is gonna hate. I hate this. UL1 and UL2. UL1 or UL2. This is so stupid. What? Why do I keep putting an E on Endel? Yay! I did the smart brain. You can't nest nested comments in comments, but you can nest single line comments in multi-line comments, right? It's fine, right? That's fine. I'm a genius. I'm a genius. I'm not a genius. How long is the size of operator? Please don't be a long chapter. It's okay, it's not long. It's not long. It's not long. We'll do the size of, but we're not doing the comma operator. Because I remember the size of. You use it to use it with malloc to assign a specific amount of memory for specific variables, etc. Although I think a lot of the variable assignment stuff already has a malloc line in the stuff. Otherwise, you wouldn't have them. They wouldn't. I'm drowning. They would. I'm not drowning. Don't worry. They wouldn't work. You wouldn't have any memory. It has to allocate some memory, right? When you do an int. But I mean, if you're working with custom stuff, like if you want to make a buffer, Okay, so the only instance of me actually seeing malloc actually used for an actual purpose rather than just being in a classroom setting. Jesus, what the hell? Being in a classroom setting and being like, oh yeah, malloc allocates memory, and then you can use size of to allocate it the memory, the size of the thing that you want to allocate the memory to. And it's like, okay, but I can just make an int. Look, see, I just made a long there, and that I didn't have to assign that memory, did I? Oh shit, we're not typing any of this out. Size of operator returns the size in bytes of an expression or a type name. The operator is right associative. The result of size of is a constant expression of type size t. The operator takes one of two forms: size of brackets type or size of expression. The second form, size of, returns the size of type returned by the given expression. Size of operator is unusual in that it does not evaluate as operand. Okay. What? So we got sales data, comma, star p. Size of sales data, size required to hold an object of type sales data. Size of data's type, i.e. size of sales data. Okay. Size of p, size of a pointer. Size of star p, size of the type to which p points, i.e. size of sales data. Size of data.revenue, size of the type of sales data's revenue member. Size of sales data, : revenue. An alternative way to get to the size of revenue. Okay. So, yeah. Well, that's excellent. Under the new standard, we can use the scope operator to ask for the size of a member of a class type. Ordinarily, we can only access the members of a class through the object of that type. We don't need to supply an object because size of does not need to fetch the member to know its size. The result of applying size of depends in part on the type involved. Size of char or an expression of the type char is guaranteed to be 1. Size of a reference type returns the size of the object of the reference type. Size of a pointer returns the size needed to hold the pointer. Size of a dereference pointer returns the size of an object of the type which the pointer points. The pointer need not be valid. So you can have an undefined pointer. You can have a null pointer. If it's a pointer to an int, it will tell you how big an int is. You may as well use size of int. However, you might not know that the pointer points to an int. You might need a container for the value of that stuff. So you can use size of, and then the pointer, the dereference pointer, the star operator on the pointer, the value of the pointer, and it will give you exactly how big a space of memory you will need to put that thing into. Very good, very handy. Size of string or a vector returns only the size of the fixed part of these types. It does not return the size used by the object's elements. So that is a Is it a pointer to a char? So it'd be the size of a pointer, maybe? Because the size of returns the size of an entire array, we can determine the number of elements in an array by dividing the array size by the element size. Constant expression size t sc, size of ia divided by size of star ia. In array 2 sz, okay, returns a constant expression. Right, yeah. Because size of returns a constant expression, we can use the result of a size of expression to specify the dimension of an array. Absolutely fantastic. And that is all I have time for, really. 50 minutes? That's close enough to an hour, really. We've learned a lot of good stuff today. We did the bitwise operators and we went over size of because it's familiar to me. And I like size of. It's a nice function. It's a nice man. Or maybe not. I don't think it's gendered. I think it's probably just a bunch of electrons. Or lack of electrons. Anyway, that's all we have time for today. So thank you for joining the live video. If you joined the live video, thank you for watching the video on demand. If you watch the video on demand, and as always, we'll see you in the next episode. Start to check I was recording that one because I changed my settings. I was worried there briefly, but it's all recorded. Don't worry, there is a VOD for this.